Hey there, this is Mark back with the last segment for this Tandy Retro Show. This is Henry Strickland, otherwise known as StricK, long time OS9 user. And give a little background on that, if you can, Henry, about how you met OS9, because it's a very interesting story. Um, and he's going to show us his single board computer, I guess he's working on. It's going to be very cool. And I'll turn this over to Henry. And thank you very much for everybody watching us. Go for it, Henry.
Okay. Yeah, so my name's Henry Strickland. Friends, some call me Henry and some call me StricK. I go by both. Um, I got into using OS9 at Georgia Tech in 1982. The professor, John Peetman, ran the microprocessor-based design lab. It was not our class, it was a 4075, which would be a senior level class, but I did it as a sophomore because I was too excited about the material. And he had source code for OS9. It's what we now call the what are the three letters for a vendor maintained anyway, it's a version of level 1 that we do have source code to, where we've lost the source code for some of level 1. And I built my own 6809 based computer, which would roughly be like a CoCo 2. It had 64K of static RAM. It used the chipset of the VDG and the SAM and the 6809. And I ported OS9 to it. It had a small boot ROM, like I think 256 bytes, and that was enough to load a sector off of a floppy and jump to it and get OS9 booted at that point. I knew of Radio Shack color computers at this point. I don't think that OS9 had been ported, or they did it at the same time as I did, and so my boot mechanism was different from theirs. Henry Gernhardt, wave to me if you hear me, right? Okay. All right, we're good. So before I start showing you some slides, while I've got the camera on, I'm going to show you some boards. I'm building I'm going to call it a single board computer, because here's a single board. It's got, let's see, here is a Hitachi 63C09E. So the C means it's a 3 megahertz part. The E means that the clock is external, and that's going to be very important in this design. And on the other side, a Raspberry Pi Pico. And there's 8 glue chips on here. And since this was my first board and I was still in experimental design and debugging, everything is through-hole technology. So I did all the soldering on this one. The next board that I've got is this one. This is my current one. And now you see there's 3 Raspberry Pi Picos. I'm really only using one. I'm using the one with the Wi-Fi. It's got the little silver box on it. We still have the same Hitachi 6309E CPU, and the glue logic has been reduced to 4 chips now, which are in this row here instead of 8. I got rid of 4 chips in this redesign. My next design, I'm going to try to simplify it down to the minimum. I'll only have 1 Pico on it instead of the 3, and I'm going to try to do it with 2-layer instead of 4-layer and make it really cheap. And while the camera's on, let me show you a couple of other things. This is the Neo 6502 by a company in Europe named Alimex. And these cost about 30 euros. And the 2 chips, the 2 bigger chips on here, one is the RP2040, which is the chip that's on the Raspberry Pi Pico. So the same modern microcontrollers on my board. And then on the other side here is a 65CO2. So they're doing the same thing that I'm trying to do. One chip, well, theirs is not quite as vintage as mine. Theirs is on a surface mount device, but one vintage CPU and the Raspberry Pi Pico's processor to do everything else. And this is a beautifully made little board. It's got all kinds of I/O, and it's very professionally done. And notice the 3 glue chips that they have here as well. Those are the exact same model as my glue chips that are here. 74 low voltage CMOS 245s. So they're doing a very similar thing, and their price point is like $30, which I'm not going to be able to get as much stuff on for $30 as they did, because they did more people are interested in 6502s, a more mass market thing.
Also,
I'm sorry?
Western Design Center is still making 650 CO2s. That's why they have those. They make a 14 megahertz version. Yeah, we don't have anybody doing that for us.
Here's a bag of 50 of the Hitachi chips. These were less than $2.50 a piece in quantities of 10. So I got like a bag of 50 for, I think, $120 or something. Look on eBay. And there's newer versions of the Pi Pico coming out. And this one's really interesting. This is the Stamp XL. It's got the 2350, the new version of the microcontroller, but it's on a board that's able to output all 38 or 40 GPIO lines by doing the top and the bottom as well as the edges. And when these are more available, it's going to be really interesting. Right now, they keep running out of them, and that's a developer board to put that XL stamp on. So that's a hint of future things. Now I'm going to flip over and present. So share screen, use a window, and why isn't it asking me which window?
Either share a desktop or an individual window.
I want an individual window. Use system window capture. But I thought it was going to show me a list of windows.
Usually it shows you a checkerboard thing of all the various windows you have open.
Yeah. Where is that?
Ooh.
Unless they're minimized, then it won't show them. So they have to be active on the desktop to share.
Okay.
Okay, it is active. I'm going to exit and try again.
I can also unpin you, see if that makes a difference.
This is kind of crazy. It was here when I did it earlier when I was practicing. Do I have to say advanced? No. Basic. Oh, now it's asking me. Okay, I had to go ahead and say share without knowing what it was going to share yet. And I choose this window, share. Okay, how's that look?
Yes. I guess we have all your browser.
Okay, whoops, go back home. So my design, I'm calling it the TFR9. TFR is a opcode that's kind of unique to the 6809. On any other architecture, it would be called MOV, MV. But for some reason, it's called TFR on the 6809. And the instruction set was defined by Terry F. Ritter, I believe. And we can ask him what TFR means sometime. And kind of like a PDP-11 is, there's a bunch of different computers that are PDP-11s. I'm going to have a bunch of different things that are TFR9s. So the 901 and the 903 are the two that I showed you earlier. The 903 is my current one. And I think I'll name the next one the 905. There actually was a 902, but it never got made. It got designed, and then I realized, hey, I can do a whole lot better, and I did the 903. my corner of modern retro. The phrase modern retro is getting applied to a set of computers like this. And I always liked Stevie Stroh's motto that there's no wrong way to retro. Everybody can make a different set of choices for where they want to be pure and where they can use modern fakery. And my choices are, I want a genuine 8-bit CPU. I like having the Hitachi chip on there. And I'll go with modern everything else. And in fact, that PiPico has a USB cable that goes to another modern computer, and that can be the keyboard and the screen and the disk and the network access. My goal is to make these really cheap, like in the range $15 to $30. And so far I've got it running Nitros 9. I've had it running level 1. Currently it's running level 2. And I had hoped to have some Radio Shack Basic running by now, but I don't. It also, I want Flex and Fusix and everything else to work on this. I've already showed this to you, but there's the 901. A nice picture I took. Here's the 903, the way KiCad imagined it's going to look without the picos attached yet. And here's how it ends up looking. This is almost like the card I just showed you. Notice there's 2 bodge wires, and then there's 2 other wires which are just going to the oscilloscope. The blue wire is a ground that I had soldered into that ring, and the white is an oscilloscope probe. But the green wire and the orange wire, those are covering up for mistakes. And I actually made my pull-ups pull-downs and my pull-downs pull-ups. And not a huge mistake, but 2 wires had to get added. And my parts list right now, the 63C09E, the Raspberry Pi Pico, and you could put any version, the Pico W, the Pico Normal, the Pico 2, the Pico 2W I think is coming out. Any of those 40-pin versions are compatible. But that Stamp XL that I showed you, that's not. The one that I really like that has a lot more GPIO pins. I'm using 245s for bus multiplexers and level converters. The Hitachi chip runs at 5 volts, the Pico runs at 3.3 volts, and these help with level conversions because the first version of the Pico is not 5-volt tolerant. It's nice that the next version of the Pico 2 is 5-volt tolerant. But I need multiplexing anyway, which is the other reason the 245s are in there. Printed circuit board. I think my next one's going to be 2 layers and easily fit within 100 by 100 millimeters, and so you can take the economy route to making those. And here's a little comparison of this modern retro territory. On the left-hand side, the 6502, here's 2 example machines. The 8-bit guy on YouTube, who's fantastic, has done the Commander X16, which is a very admirable board. It's pricey though. The developer edition's $350, I believe. And that's a 65 CO2 running at 8 megahertz. Now, 8 megahertz on a 6502, I think is comparable to, is it 4 megahertz or 2 megahertz on our machines? I mean, they have a different style clock, and it gets counted differently. And then the one I showed you, that Alimex red board, I misspelled it Amilex here, it's Alimex, is $35. And so by using an RP2040 instead of all the other support chips and RAM and ROM and IO devices and everything else that's on the Commander X16, they divided the price by 10. And I actually got one. I I wouldn't care enough about 6502s to get a Commander X16 myself. But for $30, $35, oh yeah, it's worth it. It's a cool gadget. Now on the right-hand side are comparable machines. The Phoenix Retro Systems F256. This is the one that Boise has been working on for the past year and is very excited about, and it's a beautiful board, but it's also in that $350-ish price range. It uses an FPGA for the 6809, and I'm attempting to divide that by 10 to $35 or by 20 down to $15 with my TFR 9. So that's where I fit into this picture.
Hey, StricK, I have a question from Curtis about your, he says, I think you said you're running the 6309 at 2 megahertz.
I'm running it as fast as I've been able to with memory mapping unit emulation on. I have not gone back and measured it without that. I think it's going to run level 1 even faster if you emulate a CoCo 2 instead of a CoCo 3.
Yeah.
So
yeah, Curtis. Curtis continued with, is that sharing read writes, or is that a 2 megahertz B part versus a 3.3 to 3.54 megahertz C part?
I'm measuring with my oscilloscope, and I see it kind of in the range of 1.8 megahertz average.
Okay.
But the deal is that the clocks are not coming out of a crystal. The clocks are coming out of code in the
from the RP
in the Pico. And sometimes that code has more work to do than other times, like if it's doing a disk access, and then I go and send a lot of data around and the clock quits running. So it's a weird situation that you're not used to. And some things that you can do on a real CoCo, you're not going to be able to do on this because you can't count on the timing to be smooth and regular all the time because of that. I'll show you some oscilloscope in a bit, or remind me to. So here's an outline of costs. 6309s, less than $5 in single quantities usually, and less than $250 to get a lot of 10. Pi Picos, I think the normal is $4. The new one, the Pico 2 is $5. The old Pico with Wi-Fi is $6. So you're in that ballpark. Getting the Glue Logic is about $1. And I think printed circuit boards are going to be less than $3 in quantities of maybe 20 or 50. It's kind of hard for me to judge what JLC PCB is doing, the way they charge you different amounts at different points during your uploading the design. I try to figure it out, but I'm not sure. So I could claim this is $15, but that's not having the 2 DIP 40s soldered on. I mean, they'll surface mount for me the LVC 245s, the capacitors, the resistors, stuff I didn't even bother listing. But you have to go into hand soldering mode or something, and they charge you more to do the DIP 40s. So I'm going to price that out, but we may have 2 paths to go, one if you want to solder and one if you don't. But everything but those 2 dips would be soldered.
Hey, StricK, I got a comment and another question.
Okay, good.
So Mark Siegel of Tandy Radio Shack said it's not a real MMU, so there should be no difference. I don't know if he's talking about timing or about.
I'll show code later to show you what I'm talking about.
So question, Joel AV says you probably get into it, but how does the $35 option compare to the $350 option with respect to video and sound?
Yeah, excellent questions. Probably video and sound is going to be sound probably is not going to work, and video right now, if you don't put a second Pi Pico on, then it's got to be done by your PC that the USB is connected to. That's why I've got a second Pi Pico on my current design, is to generate video, and a third pico on my current design for sound. So if we raise the price up from $15 to 25 or 30, we can probably be doing all that for about $30.
Do you want me to interrupt as these come up, or you want to wait to a certain point, or hold questions to the end, or what do you want to do?
No. Keep asking. You're doing good, Mark.
Okay. All right. Just asking.
Mm-hmm.
I have a question.
All right.
Okay.
Why did you choose the E version and not the standard one? Seems to me like if you had the internal clock, you would have saved on chips.
Actually, no. Look at this picture right here that I'm presenting. Shows the 6309E on the left and the Pi Pico on the right. So two of the pins on the Pi Pico are providing the E and the Q clocks to the 6309. And that's actually important because there's code running on the Pico that I call the outulator. It's not emulating a 6309, but it's emulating everything on the outside of the 6309. It's emulating the clock, it's emulating the ROM and the RAM and IO devices. So this is an outline of all the different signals that you need to operate a 6309. And I should have put the letter E on there because that's actually real important. The E and the Q clocks are inputs instead of outputs to the 6309.
In case you didn't know, Henry, Frederick is actually building a single board 6309 computer also.
Okay, yeah. But anyway, no, there's no external clocks, or I don't need the two flip-flops that Motorola always shows you. That's going to be in the programmable IO code.
Yeah.
Yeah. So the 16 address buses that always go out from the 6309 to the Pi Pico. There's also read-write and 5 other status lines that are coming out of the 6309. Those 5 are advanced valid memory address, last instruction cycle, BA, BS, and busy. And so I get all of those into the Pi Pico. The data bus is bidirectional. And then there's these control lines: reset, interrupt, fast interrupt, non-maskable interrupt, and I've got pins that are dedicated to that. But if you add up the number of pins, the number of signals coming into the Pi Pico, it's more than the GPIO that's available. So here's how I multiplex it. I take the first 16 GPIO lines, numbered 0 through 15, and I call that my general purpose bus, and I'm going to multiplex things on it. Those chips down the middle are the bus driver multiplexers, the 245s, and G18 controls the top 2 as the output enable. So with G18, I can say, I want to read those address lines on G0 through G15. The bottom 2 middle chips are controlled by G19. And that turns the read-write and the other status lines and the data bus to get mapped over to the Pi Pico, where it can read it on the same G0 through G15. And then G20 is the direction, because data bus is bidirectional. We can change G0 through 7 into outputs from the Pico and turn the direction on the 245 so that it's output back to the 6309 on a read cycle. When I say read or write cycle, I'm talking about from the point of view of the vintage CPU. Then G17 and G16 are the Q and the E signals, and G21 is reset bar, G22 is IRQ bar, and there's about 4 more G pins that are available that you can put on fast interrupt, non-maskable interrupt, things like that.
Henry, I have another question from the audience, and I have a question myself.
Okay, go.
So Daddy Burrito says, so are aftermarket 6309 chips expected to be compatible, like something that can be bought from Jameco or somebody like that? Aren't those usually just old new stock?
I think it's all old stock, and I get them from eBay. I just type 63C09E on eBay and find the people that are selling them in large quantities for cheap instead of individuals for expensive. I
Right.
don't know the story behind them. There was a conjecture that Hitachi made a big run as automotive parts at some point. I have no idea if that's true.
I do know that there's a manufacturer supplier, and I'm trying to remember the name. It begins with an R, but it's not Rockwell, something like
There's
that.
a UT source also that sells them.
But yeah, UT sells shows a lot of new old stock. But there's a company begins with R, and I understand they get licenses to manufacture like old silicone like that, and so
Mhm.
they're kind of expensive, but they're new based on the original designs.
Yeah, there's a surface mounted part that if you look on JLC PCB and their parts, there's a surface mount part that they charge you a lot of money, like I don't know, 10 or 20 or $30 for.
Rochester, thank you, Alan. Yes, Rochester
Yeah.
is the one. Yeah, I
So,
guess they make new. You get the design. They
mhm.
not lease, but they license the designs, and they'll make new silicon. Uh, with the old designs. Here's my
Mhm.
question. Um,
That's a
doesn't the RP 2040 doesn't have any like hardware PWMs?
Yeah, it has PWM output, so if we had extra pins, we could use that to
Right, for the E and
produce
Q clock.
sounds.
Well, you could use it for the E and Q clock because most of those hardware PWMs are all done in a dedicated circuitry. So once you set them up, they just run independent of the rest of the
That's
process.
right. And it also has clocks on it. Like I use one for a 60 hertz sync interrupt, which OS9 likes. Um, but I'm going to show you my E and Q code. It's more complicated than that, what I'm doing.
So Paul Thayer, yeah, I've heard the same thing that there's still some big demand for the 6309, and so that's why it's still being made. It's more available than one other things.
Okay. Yeah, I don't know the story, but I'm happy. All of mine end in EP, E for external clock and P for plastic dip, and they all look the same, like they're from 1982 or something. All right, and so while we're talking about the external clock, here is a typical read or write cycle, and this would kind of count both for the 60 for the I'm sorry, for the version without the E as it does for the version with the E, and it's the same on the 6809E as well. But at the beginning of a cycle, E and Q are both low. And then a quarter of the way through the cycle, you raise Q. And another quarter of the way through the cycle, you raise E. And then you lower Q. And then you lower E. And that lowering of E almost ends the cycle. But it's actually the signal to all your I/O and your RAM and stuff, and to the CPU as well, that now's the time to latch data, whether data is going in or out or to memory or to I/O or whatever. It's on the dropping of E that everybody drops their data. And so the data sheet says, go ahead and hold the data for an extra 30 nanoseconds after the drop of E. So I've drawn a little bit of an extra line with E low over on the right-hand side to show you that the cycle's not really over for another 30 nanoseconds after the drop of E. And my Pi Pico is going to have code to make the E and the Q work just like that. But interlaced with that, we have to do other things. So around the time that Q rises, my Pi Pico is going to read the address that's being put out of the 6309. And to do that, it's got to do two things. It's got to make sure that the general purpose I/O pins 0 through 15 are on input mode, and it also has to make sure that that middle chip is enabling for the address bus and not enabling for read, write, and data bus. So all of that happens about the rise of Q, and you really have to set things up in advance of when you actually read. And this is going to be done in programmable I/O. There's these little state machines called PIO that are like their own little processors, but with very strict timing, very simple instruction sets. Kind of lame. You have to be kind of creative to make them do what you want in a lot of cases. And it took me a little fiddling to figure this out. But when it reads that address inside the PIO, it then shoves it into a FIFO. There's a 4-stage FIFO. These are 4 32-bit registers between the programmable IO and the ARM core that's running my main C code inside the PyPico. And so it reads that address and shoves it on the FIFO. And then on the next one, when E rises, we have flipped the chips around so that we're now going to read the read write and the status lines and shove that into the FIFO to the main CPU. The main CPU is in a loop, and it was waiting for that address to be ready. And then it's waiting for the read write pin and status lines to be ready for it to read. And so at this point, it knows the address and it knows if we're reading or writing inside the main CPU, and it's going to take a branch to what happens next, depending on whether it's a read cycle or a write cycle. The programmable IO also takes a branch because read is much simpler. A write cycle is much simpler than a 6309 read cycle. On the write cycle on the top, on the right-hand side, you see it just says read data. Somewhere after long enough that you know the data is settled on the data bus, you read the data and you shove it into the FIFO to the main CPU. So that's a write cycle, which means the main CPU, if your address is in the range of ROM, you're going to ignore it. If your address is in the range of RAM, the Pico is going to update its RAM array. It's got an array of bytes in the C program that simulates the RAM. It'll write that data to that address in that internal array in the Pico. But if it's a read cycle, then we have to change the GPIO pins 0 through 7 to outputs, and then output the data, and then drop E. Remember, dropping E means that we're outputting the data, and this is the time for you, the 6309, to read it. And then we have to change those GPIO pins back to inputs again and get ready for the next cycle where we're going to read the address. And the main CPU, the ARM core that's running C code in the Pico, has an if statement on that read write bit, and in the lower half, if it's a read cycle for the 6309, then it has to output stuff back to the programmable IO thing for that output data, but also for the data direction register. So it actually writes 3 bytes. First, the data direction registers to make those GPIO pins outputs, then the data itself, and then the data direction to flip it around again. And I'll actually show you that code in a while. How are we doing? We're halfway through. Okay, any more questions at this point, or let me plow forward then. Here I just wrote down again what the GPIO pins on the Pico are being used for, but that's the same thing that you saw earlier. Now there's a USB cable going to your PC. Could be Windows or Linux or Mac or a Raspberry Pi or a Pi Zero. It's also powering the single board computer, so there's not a separate line for power. It's all done through that one USB cable. And on that modern computer, there's a program called T-Console. It's written in Go, and therefore it'll compile into a very simple static binary that'll work on Linux, work on any of those architectures. And it's the keyboard and the display for the machine right now. I'll give you a demo. I'll show you a session where it's working in a while. And it also is acting as the disk drive. And so Not only is like character data going through it, but packets of disk data are going over the USB cable, and lots of logging information can go over the USB cable. I can get a trace of every single machine cycle, be it a read or a write, for debugging. What about Wi-Fi? I'm using the W version of the chip, so I could be doing something with Wi-Fi, but I haven't used it yet. We did have problems at the Vintage Computer Festival in Mountain View last year. This is with Thomas Shanks's CoCo board that had a PiPico W. And in that noisy environment with all that stuff going on and all those networks, it was not able to get on the network we wanted and be usable. We don't exactly know why. It makes me a little nervous about trying to demo this in the future with the Wi-Fi on. So we don't know how that's going to go yet. There may be some hardware tricks, even just better antennas that we can do.
Faraday cage and your own access point.
With that actually might be the way to do it at a festival or something, is to Faraday cage it. Yeah. But if Wi-Fi is working, then you've got a single board computer with Wi-Fi. Add a display, add a keyboard, put it in a little box of some sort, and you've got a laptop that's running OS 9, and you can go to Starbucks and pop your email or something. I'd love to see that day. Here's where I mentioned that there's 3 Picos on my board, and I've only been talking about one of them. The second one is reserved for generating VGA graphics. That's going to be fun. I look forward to doing that. It'll be watching everything the 6309 does, be watching all the communications to the first Pico, and keep track of all the writes that are necessary to understand what's supposed to be displayed in graphics, and then have programmable I/O machines displaying those graphics. And if you use the Pico W, you can get something closer to HDMI output, because they have more special hardware for that on the newer Pico 2, I mean. And then the third is for whatever, like sound. So that'd be neat if we can do all that. I think I'm going to stop at this point and give you a real demo to watch, and then I'll come back and show you some code. But this should be a little more fun to actually see something working. So let me plug my machine back in, because I had it on.
You are the last presentation, StricK, so if you go a little long, you're not going to be
Okay, yeah, we're going to try not to, but thank you for the offer. I am now, let's see, let me stop the screen share for a moment. Okay, so I have a cable with switches on it here for a USB hub, which is really convenient. Otherwise, you have to plug these in and out in order to reset and reboot. And just flipping the switch is convenient. So I'm going to hold down the little button that's the bootload button while I power it up by flipping that switch. And it made that sound, which means that it has mounted itself as a disk drive. And I'm going to share a terminal window, share screen, do one window, share, choose this window and share it. Okay. And run make. And that will spin for 15 seconds or so. But eventually it will, right now it's copying the binary onto the Raspberry Pi Pico. And now it's opened up a terminal to it. And you see OS 9 booting, and the startup has it going into BASIC and running a program there that's a benchmark. And after 5 trials of how long does it take from the open brace to the closed brace, it's done it at an average of this amount of time. And I keep this as a constant benchmark to make sure I don't get things slower and slower instead of faster and faster as I try to make optimizations and improvements. My screen's very readable. Good. Directory of commands. We've got all the commands there. How much disk is free? I made a pretty big disk for this demo. How much memory is free? Well, if you look at my mmap, I'm only doing a 128 K memory instead of a 512K memory. That's because this version of the PiPico only has 256K of RAM on it. The PiPico 2 has twice that, and so we'll get closer to a 512K at that point. But let's see, I can also show the SMAP that this is the map of the kernel's memory space, and a lot of it is still free. So plenty more kernel modules could be loaded there. Like I haven't loaded pipes for some reason. I should have done that. And PMAP shows which of these available memories is getting mapped into which slots in the program. So this is what OS 9 level 2 does, is each of these processes, the PMAP process, the shell process, and the kernel can all have their own 64K memory space. And if I pop into basic and on 09, and from here I shell out into a shell, and from here I ask for the PMAP or type proc, you can see that that's my original shell, and I went into basic, and then I shelled out into a shell, and then I ran PMAP. And on each of these, this bottom page of memory is different because that's the read-write data for the process, whereas a lot of these upper pages are shared because OS 9 is good at sharing read-only modules in memory between different processes. And there's also procs, which is similar to those, but I can exit out of this other shell, so it pops back into basic. And in basic, I could write code like 10 for I equals 1 to 100, 20, print I, 30, next I, out of the editor, list it, run it, and then I could even pack it into bytecodes that later, when I leave basic, and I'm back at my shell, and I'm not running basic anymore, but I say program, because I forgot to give it a different name than program, and it runs the packed bytecodes. That's the same as what it uses as the run B is for running bytecodes. Like that. So I don't know how many of y'all are users of OS 9, but there's this cool stuff in here. Let's run the disassembler on the delete command. And in here we look for the OS 9 calls, and there's only two of them: delete the file and exit. So that's short and sweet, and that short and sweetness is what a lot of us like about OS 9. Is there anything else I want to?
Hey, StricK?
Yeah.
You got a nice compliment from CoCo about tackling this project, and then Curtis also said, feel free to grab the 6309 optimized version of Basic 09 from EOU.
Oh yeah. So my CPU type so far is still running in 6809 mode. So actually switching things and doing a 6309 mode is a future project. But this is as far as I've gotten. IRQs. Show me the IRQs. And What else is flashy? Oh, showing the T mode. That's the this is like the ioctals on the STTY command in Unix to set your baud rate and stuff like that. A dump. Let me list the startup file, because I told you that on startup it went into basic 09. Oh, you've noticed it's also like echoing whatever I type. That's just a setting. We startup had it go into basic 09, had it go into the editor, typed in this program, quit the editor, and ran it. And my console recognizes the open brace and the curly brace. Why is that sitting there? I don't know, but yeah, that shouldn't be there. That should get added by the console program that's doing the timing for me, just as a courtesy, as an extra feature. Okay, good enough. Anyway, you see it running. If I hit oh yeah, let me do one more thing. Let's something that takes a long time. If I disassemble commands basic 09, it takes forever. So I can control V, control C, and now I have sent a control C to OS9. Whereas if I actually do a control C without the control V in front of it, I've killed the T console program that was talking to the single board computer for me. All right, so now that you've seen it actually running and working, I'm going to flip back to my other window. Stop share, and let's see. Yes, his initials, you got it. I was looking at the internal chat here, Paul. Right, TFR.
Yep.
That
was my guess too.
Yeah. As a story I got from John Peetman is that there were two opcodes that Terry F. Ritter put in that he was proud of, and one was the TFR and one was the SEX. Okay, now I'm going to share this again.
Just like all good 13-year-old boys.
Yeah, yeah. You know, and Knuth kind of made the same comment when he designed MMix, Millennial Mix. He said everyone who designs instruction set is allowed to put one crazy instruction in there. And so Knuth's was the 64-bit by 64-bit binary matrix multiply instruction that he put into that instruction set. Here is C code to run in the main processor. So reset does not have to be fast, so I don't use programmable I/O for it. Instead, I have this C function. And so it goes through the first 20 GPIO pins and sets the direction either to input or output, depending on which group they're in. And then there's these other 5 pins. And notice there's a gap in them, so it's not just a simple counting loop. Those we all want to be outputs. And so now that we've set the directions correctly, we can assert reset, which since it's negative logic, I had the word not. So that asserts the reset. And while reset is down, I say enough cycles to reset is 60 cycles. I do Q and E down and then Q and E up, and I cycle through that 60 times, and then I can let go of the reset, and that works. So this is an example of code that I put in the outulator to control the 6309, and main will call this. Emulating RAM. this actually looks a lot more complicated than it is. To do a CoCo 2 where there's no memory mapping unit, I just need one array that's 64K long, and to read an address, we return the RAM at that address. And just for a little bit of safety, I'm making sure my address doesn't go outside the bounds of the array. I really should have an assert there and catch any code that's passing bad addresses in. And similarly to write, I set the byte at that array to the data. And these extra things are here so that it follows the same protocol that's needed for a CoCo 3 where you have the MMU. And here's that code. So a different class for the big RAM, and we have a much larger array. It's now 128K of RAM instead of just 64K of RAM. So that's our physical RAM. And we have the MMU, which knows two different tasks, a task for kernel and a task for user mode is how OS 9 uses them. And the 8 different 8K blocks all have a byte to tell which block in here they're mapping to. Then you also need the bit whether the MMU is enabled or not. That's a control bit on the CoCo. And which the current task is. And on the normal CoCo, there's only 2 tasks, 0 and 1, but some other machines might have more. And as an optimization, I pre-compute some stuff in here, and I have a pointer to task 1 or task 2, task 0 or task 1 out of that. So we can ignore the optimization. And I don't even know if it optimizes, if it makes a difference. I need to try it, taking it out. So to read or to write, there's an extra line in here. First, we have to convert the address to its physical address, which will be only 0 through 64K. And both read and write call the same thing before they either set the RAM or read the RAM. And so what is this logical to physical? First, I do that safety measure again. Then I shift the address 13 bits to the right so that I only get the top 3 bits, and I call that the slot that it's in. It's one of 8K slots. And from the lower part of the address, I get the low 13 bits, which are the offset within the block. We only use the MMU if the MMU is enabled and the address is less than that value. I'm not emulating the bit yet that turns on or off the FE page feature. It's just kind of hardwired with it on right now because that's what OS 9 does. So what block are we in? It depends on whether we're using the MMU. If we're using the MMU, we look it up. Otherwise, this is the formula to find it. And pre-fizz and fizz, I guess it's, that looks like I was debugging something and I was printing that once and it's a dead variable now. But anyway, this reassembles which block you're in with the offset and returns it. So that's what I talk about when I say the outulator is emulating the MMU or not. Let Mark Siegel ask questions if he's got more questions about that. But you can see that executing this code on every read cycle or every write cycle, that's a lot more code to execute on the ARM core inside the C code inside the Pico. And that has to be executed before the results are sent back to the 6309 CPU, and that delays things a bit. So the programmable I/O, this is the unique feature of the Pi Pico and why we choose it instead of the ESP32 or the this or the that or the various others. And turned out that back on this previous page 4, 5, 6. Yeah, let me go one more. 7, 8, there. G16 through G20 are these side effects for the E and the Q, and for turning on and off the bus arbitration multiplexing chips. There's 5 of them, and that was very convenient because on the RP2040 and the Pico, you can have up to 5 side outputs, which is where this word side appears. And so they're controlling the E signal, the Q signal, the receive address or receive data or send data pins or combinations. And this is where I show what the numbers are going to be that follows the word side. And so I say we're going to have 5 side sets on every instruction. And here's the very first is a no-op with a side of 2-4. All right, 2-4 means you're in phase 1 and you're receiving an address. So phase 1, we want to output 0, and receiving an address, we output 24. So 0 and 24 makes 24. And when that 24 changes to a 26 there, that means that we changed to phase 2. And so instead of that 0, we're adding that 2 to the side output. So what happens is the state machine executes no up, no up, no up, no up. Now it's going to input a number from the pins. That's the address that we're reading. And we've been telling it in advance that we want the receive address mode. After we receive the address, now we can go into the receive data mode. We need a few no-ops. So how fast are these executing? They're at half of the 133 megahertz clock. So each of these instructions, they're 66.5 megahertz clock for the PIO, because I divided it by 2. That's 30 nanoseconds, I believe. So each of these no-ops is 30 nanoseconds, or an input. Now I read it turns out I'm reading the data, but I don't care about it. I care about read W and status. And then I'm going to jump on one special pin, and I've set up that special pin to be the read-write pin. So if we're in read mode, we're going to jump down to read. Otherwise, we fall through to write. You remember in my chart earlier, write was the easier one. All we have to do is at the appropriate time after we delay, read the data from the pins and shove it into the FIFO. That's the side effect of each of these input instructions, is that it puts it on the FIFO so that it goes to the main CPU and jump back to the top. But if it was a read cycle, we take this jump, we pull a block from the main CPU and we put it in the pin directions. Pull a block from the main CPU, put it on the output pins, and I'm sorry, it's not pull a block, it's a blocking pull. That's how I should read that. It's pulling a 32-bit word, of which we're only going to use 16 bits, but it's a blocking. And so the GPIO will stop here indefinitely until that C code has the pinders and the pins, and then how to fix the pinders, and has shoved those into the FIFO that goes back from the ARM core to the programmable I/O. And then there's an automatic wrap available that takes you to the wrap target. So that is my PIO code. You'll see some PIO code that's a lot simpler. You'll see some PIO code that's far more complicated. But that's all I needed, is that just that one.
How many instructions are you using there? It looks like you're filling up the PIO code memory.
It's only about half of it.
Oh, okay.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, and you get 32. So it's 2/3 full. But what I've been doing is I started out not having all these no-ops. I just had a different divisor. I started out dividing the 133 megahertz clock by 8. And then I started to say, I've got instructions to spare. What if I have that speed? And all right, I double the speed, so I'm only dividing by 4. And then I look to see if it breaks. And if it breaks, I try inserting some no-ops. And then I sped it up again by dividing by 3. And now I've sped it up again by dividing by 2. So my hope is that I've got fine-grained counts of no-ops right where they're needed instead of having a slower clock. And that's how I've been speeding this up over the days that I've been experimenting with it. Does that make sense?
Oh no, that makes perfect sense. I just saw that and I'm like, I've not seen PIO code that long before in one big block.
Yeah. So it got longer as I sped it up.
You might have already covered it, StricK, but where did you say you're generating the E and Q clocks?
Okay. They're in this side output.
Okay.
That 24 is a 5-bit number, and it's composed out of these pieces. So if you look at these numbers modulo 4, it's going to be one of these numbers, 0, 2, 3, or 1, and that's depending on whether you're in phase 1, phase 2, phase 3, or phase 4, where neither or Q is high or both are high, just E is high.
Gotcha.
So as we go, yeah, it starts out that 24 is mod 0, 26 is mod 2, 22 is mod 2. Here we're mod 3, and eventually we become mod 0 again, either here or here. So yeah, it's weird. It's just this word side means we're putting out signals on those 5 lines. And it's also doing the multiplex of either the address or the data, either receiving or sending, are all controlled by those side words.
Nicely done. Thanks.
Okie doke. Yeah, I mean, this is totally weird. I mean, people who've programmed but have never seen this particular chip, this is alien. So I had to learn it. And previous, yeah, next, transcript of doing some stuff in OS 9 level 2. And I wanted to do this live for you, so I showed you live. But this is what it typed as it booted up. It gave us that banner, and then as it went into basic, it does this, and that's a line feed. My terminal program displays control characters like that. It went in, it went to the editor, added the lines, and then it ran the code. And out at the ends here is the timing data that I'm always watching. I did a directory, the execution directory. I list the startup, MDIR. There's all my modules that are preloaded or loaded at this point. Extended version. Free, mfree, mmap, smap. I showed you all these things basically earlier. So, what else can you do besides running? If I slow it down a lot and do a lot of logging, I can get a step-by-step listing of each read cycle and each write cycle. And that's kind of fun to see. And if I add more smarts to it, I can have it decode what it's doing on the software interrupt 2s, which are the system calls. And so I ran and collected this log file, and I'm going to grep all the lines that say they're OS 9 calls from my logging, and I'm also on only the lines that say fork on it. And so here's the 4 things that are forked during the startup. First, it's forking Cisco, and it forks the first shell, and it forks the second shell, and it forks basic 09. And you can see the arguments coming in for oh yeah, the size of the parameter area and the start of the parameter area. Those are the inputs to fork. And then the dot, dot, dot means look elsewhere for the returns. So here's another grep on that same file for the return codes. And the returns start with fork and all of their arguments as the inputs, and the cycle number. This is the actual machine cycle number starting at 1, and it returns, and it'll show you the error number if it returns an error, or what the decoded results are that it forked process 2 or 3 or 4 or 5, and the cycle number that the return happened on, and which task we're in. So that first one was called from kernel mode, and these are all called from task 1, which is user mode, and what pages were actually mapped at that point as well. So great stuff for reverse engineering programs and debugging things. Here's a formula for what different system calls were ever called in this log file, which is just booting up that same stuff. So we use awk to pick out the field and then sort and only print them uniquely. So we can see allocate 64, allocate a task image, allocate a process structure, allocate a task, and you can look all these up to see what they do. And then there's some unknown where my console program didn't understand this. See, a lot of this is decoded by my console program, not by the PyPico. You know, like it gets the raw results from the PyPico, but then in Go code running real fast, it prints those out. And next, I'm going to show tracing some cycles. Here we're starting at the beginning of rel. You jump to 2602. This is how you use the is it the DOS command to load OS 9 and launch it off of a disk. Anyway, it jumps to 6202, and from there it goes to 6231 hex. And lines with a double at are the first time we've encountered this address and executing the opcode. And lines with a single at means that we're executing an opcode, but we've been here before. And then extra read cycles and extra write cycles that are doing data, like how does one clear FFDF? Well, look, 6809 or 6309 clears by first reading the register and then writing it. And I didn't know that. I don't know that emulators emulate that correctly, but we're running on a real vintage CPU and we're actually logging every cycle it does. And so I can see things like that. I think that's really cool. And I guess it's harder to see because it's off the screen, but we've got the actual assembly language commands and comments are being merged with this log of simple reads and writes that are coming out of the 6309. And the way we know that it's the first opcode of an instruction is from the LIC line. The last instruction cycle was asserted during that previous cycle. And so we know that we can disassemble this instruction. We're actually not disassembling, we're lining it up with the listings from the assembler. Let's see, another example, somewhere in the shell. How does a shell work? Well, we don't have good comments, but you could read through this and see how they're executed in order and how this calls that and returns, and you could start writing comments for us. And here's some, we're in the kernel, Now we're in the random block file driver, and it's going to do some return instructions here. Pulls PC, those are returns. Pulls PC, that's a return. And we're back to the IO manager. And these have comments usually. There's some stretches that don't. So this would be very helpful if I were going to go add more comments or clarify some comments as to see actual execution traces lined up like this. My suffix right here is 10 hex digits. The first 4 are the size of the module in OS 9, and the next 6 are the CRC. So I actually have a directory where I store all the IO man compiles I've ever done, and anything that's has a different CRC gets saved there, and my code can automatically find it regardless of where it loaded the stuff from and stuff like that, because I sort them that way. And that's it. So I'm ready for more questions. Oh, we did go over. Mark, you there?
I am. Just got to unmute 2 systems.
Okay.
Actually, I don't really see any further questions. They've pretty much all been asked. Lots of positive comments.
I do have a quick question.
All right.
So your outulator code that you're using there, and that all that stuff that you're pulling off of that. If I were to slap a Pico, like wire one up and slap a Pico into the cart port, would I be able to do a live and real time log like that? Are things fast enough
Yes.
that I'd be actually able to log all that stuff from the CoCo?
I think so. I think with the Wi-Fi version, you could be throwing out UDP packets.
Okay. What would I be? What's my bottleneck? Would I be buffering? Would I be buffering based on like how fast I can spit characters out the Pico and wind up having to wait for a lull or something? Or
Yeah, we'll do the calculations. Every machine cycle has 16 bits of address and roughly 16 bits of data and status bits that you actually do want to see, whether it's reading or writing, and which is a valid memory address and which is the last instruction cycle and stuff like that. So 32 bits of data per instruction at 2 million instructions per second, and then figure out what the equivalent data rate is coming out in UDP packets. And I think it's just inside what's doable when I did the back of the envelope calculation.
yeah, and if I'm using a straight CoCo, I'm probably not running it at 2 megahertz.
And
I got a question.
another thing you could do is you could spool up to 256K or 512K of data in the Pico and then spit that out. So if you have the trigger that you want, trigger on an address or trigger on a data, I think that's doable. And Thomas Shanks thinks it's doable, and it's one of the goals of his CoPico project. But anyone can build this and do it.
Frederick, you got a question, and William Athing here on the panel has a question also.
Yeah, you're going to do a VGA version of it, and are you going to do like a VDG or a gimme style graphics, advanced graphics? And also, in your sound chip, will you do CoCo style, or will you go like a PSG or Yamaha chip?
I want to do CoCo style. This is really a CoCo centric project as I see it and as my values go. So I would want to be able to run the Nyan Cat and stuff that creates noise on a CoCo, or emulate an Orchestra 90.
William's question is in the Zoom chat. And by the way, Thomas Shanks is CoCo. We covered that last year on this virtual fest, so it's the last one. Unfortunately, I think it got kind of recorded at this low bit rate, so it's kind of fuzzy, but it does have content. So.
It works.
Yeah.
William's question?
You're going to make this available for download, Gerber file, source code.
Yeah, it's all on my GitHub, which is named StricK Yak, StricKYAK, and the repo is named TFR9.
I'll make sure I get links for all the presentations been done today, and we'll get them rolled up. They'll be on the like a news notes. I'll upload to the CoCo Discord, but I'll also get them added to each of the videos, and I'll pass them on to Jim Brain so that the Glenside one, he can add the same notes to each of those videos as well. So I'll have all your links and all your contact info, because I'm sure people want to contact you and ask questions.
Well, the code is a mess, but it's there. It'll get cleaned up at some point for presentation. There's a lot of experimentation in there.
Messy code. I don't know what you're talking about.
Yeah, at least it doesn't have bugs in it. Some people write bugs.
Well, if there's no further questions, we'll call it a day, because this is the last presentation. I've been doing this since 8 this morning, and now it's 6:15, so it's been like 10 hours.
Yeah, it's been a good day, Mark.
Well, thank you. Jim Brain has already thanked me. I appreciate that. Like I told him, I said, this is just basically what CoCo Tech is about. That's something I want to do anyway. So just more of the same, just more people to schedule. Same thing. So, okay, well, we're going to call it a night here. Everybody say goodbye.
Okay, doke.
Bye.
Bye-bye.
Cut the stream.
Thanks, everybody. It was awesome.